Okay, welcome back. Sorry about that delay. Okay, what I want to look at is direct current DC circuit theorems, current sources and EMF. And I'm looking at it on the Thevenin's theorem. Now, Thevenin's theorem is used to simplify a resistance network with voltage and current sources within it. We replace the network with a single EMF E and a resistance RT in series with it. This is like replacing the network with a battery that contains internal resistance. Now that's just for the purpose of simplification, okay? But as you know, nothing is ever that simple, okay? Now, diagram F1 is our first circuit. It is the circuit we want to simplify or make an equivalent circuit. Now, you need to draw these out for yourselves. You must draw the diagram out so you get a conceptual pictorial representation in your own mind for yourselves. Do not just think you can do it from the screen. It will not work. Okay? Just pull back a little bit just to make sure we can get everything in. Okay? Right, now and here we have diagram F1. Battery source supplied across these two terminals, okay, Vs. We have R1, R2, R3, okay, as diagram F1. Now, V out, voltage across output terminals, is A and B, okay, and that's what we need to bear in mind. Now, we need to simplify a circuit that is in parallel, and obviously, if you look at it, you can almost say they're both R1. R1 would be now could be in parallel with R3. R2 could also be in parallel with R3. But that's just from my perception. Okay, it doesn't mean say it's right, but from my perception. But let's look at what we need to do to make sure that we get the perceptions correct. It is important to remember that the voltage that appears at the open end of the circuit is called the EMF, diagram F1. Now feel free to go back to diagram F1 anytime you like, it is your choice. It is referred to as the network. Remember, there would be a battery in the circuit or some source of supply. It does not necessarily need to be a battery, it could be a transformer supply if you wish. Okay. We now need to simplify the above circuit, remembering that it would have a battery, source battery at Vs. Okay, let's just go back to see where Vs is. And Vs is here. And that's our Vs. Okay? Now, to calculate the resistance total of the circuit, RT, we would remove the battery source from Vs and link it out with a short circuit, such that the equivalent diagram would then look like this. In the above network, R1 and R3 makes up a parallel circuit, and the circuit would then look like this with R2 removed. Now we're saying that R1, let's go back to the diagram, R1 and R3 we're using as our parallel circuit. And we have removed R2 because R2 in this stage will not be applicable in respect of our parallel circuit. Now bear in mind that in this case we've used this R1 and R3 to formulate the parallel network. Okay. Now again, just to recap, in the above network, R1 and R3 makes up a parallel circuit, and the circuit would then look like this with R2 removed. We have R1 and R3. R2 is no longer here, it has been taken out. Okay, this becomes diagram F2. Now R1 and R3 are in parallel, so we need to calculate these resistors using appropriate formula. Now something I've noticed here now, that I did not give any values for R1, R2 or R3. I'm hoping that I've given some values later on, otherwise I'm in trouble. Now again, direct current DC circuit theorem, current sources and EMF. To calculate R1 and R3 in parallel, looking at diagram F2, R1 times R3, I'm using the product over sum formula. Now product over sum will be R1 times R3 over R1 plus R2. Now R1 is 11k ohms, R3 is 47k ohms. Now what I'm puzzled at is why I did not put this early in the values earlier on. Maybe I have, but maybe I've overlooked it. No, I haven't. Okay, but I obviously had the information previously, so I've proceeded along that lines. And you will do the same. Okay, what I've done, I've simply cut out the middle calculations that I would normally do, because it's something from my head. Okay, right, now 11 kilo ohms times 47 kilo ohms over 11 kilo ohms plus 47 kilo ohms, and those are the figures that I have. This will give you 8,913.k. My apologies. This will give you 8,913.1 ohms. We need to convert that to kilo ohms, so you will divide that by 1,000. Therefore, it will then be 8.9138 kilo ohms. And this is the resistance or the value in resistance in parallel. Now you need to have done this for yourselves. Put this into your calculator. Make sure that you have arrived at the same solution and values I have given. Do not take it as read. I could have put this in simply off my top of my head because I have no hair already. Okay. We now need to calculate R2 plus the total resistance of the parallel circuit. So here we now put R2 back into the circuit with RL, the value that we have calculated previously, and RT will come up to our total. Now this is now a series circuit. As you can see, RP is in series with R2. A and B is still remaining our output, and this becomes diagram F3. Draw the diagrams out. Put in the values. Do not assume you can do it just off the top of your head. You're not as clever as I am, and I have problems. Thank you. Okay, RT equals R2 plus RP, 22 kilo ohms plus 8,913.8 ohms. Okay, or convert that to kilo ohms again, and you'll find it comes up to appropriate values. Now, this is now our final resistance of the circuit. We now need to find the voltage across the previous parallel network. I'm just come back a little bit, make sure I could get everything in. Okay. Okay. Now, R3 times Vs over R1 plus R3. Now that becomes 47 times 10 to the 3 times 12. (11 times 10 to the 3 plus 47 times 10 to the 3. Now again here, I believe 12 is all supply voltage that we apply to the circuit. But I'm a little surprised that I didn't actually put this in earlier. My apologies. Okay, but you can see that when you have put this into your calculator, it should come out to 564,000 over 558,000. Make sure you get these values correct from this result. That then comes to 9.724 volts. This is the voltage across the parallel part of the circuit. Because the load would be in parallel, this is the voltage across the load. Now, all I've done here now is going back to this diagram. That diagram has now become 1 because you have to add that resistor to that resistor to bring you to F4. And you'll see, if you look at diagram F4, and I believe it's F4, you'll now see you have a single resistor which represents all interest. Okay? And that's V out, again A and B. Okay. Now we are going to put a load of 10k across V out. This would then give us a total resistance of 30.913, and look back at where we got 30913 from, and you'll see it came from, good question, it came from here. Okay, it didn't just appear by magic. I am not a magician. I may be many things, but I am not a magician. Okay. Now we're going to put a load across the output, and this is where we're going to put the load across here, A and B. Okay. The load could be anything, but we're just going to use a 10 kilo ohms load. Okay. We now need to find the current. Putting that I equals V over R, you'll see that that gives us that, and you'll see that 2.3767 times 10 to the 4. Okay. Gives us 0.238. Now I've put that as milliamps. Now I believe that should be amps, but I must have done that for a reason. But you have to bear with me that the reason would have been long lost by now at this point in time. But it could be right for 0.238 milliamps, because it is 10 to the 4. But make sure you've put it into the calculator and you have arrived at something to this. Now, if you follow the formulations, there is no reason to get this wrong. Voltage across the load is now V equals I times R equals 0.238 times 10k equals 2.38 volts. Let me just come back, make sure that everything can be in shot. Okay. And that's it. Thank you. I hope you found this useful. And again, you need to write out the information for yourselves. You need to apply it in your own way. Let me just go back slowly so we can make sure everything is in shot. Again, do the calculation for yourselves, put it into place. Okay. Now I'll simply zoom in on this. Actually, I haven't made anything larger in any shape or form, but I've just zoomed in on it on screen. Hopefully it will be adequate for my viewing when I come back to play it back. Okay. Now look where the diagrams have come from. Look at the values of R1 and R3. Look at the resistors we chose to form part of our parallel circuit. Make sure you have replaced the relevant components in place. And remember the original circuit that we had, that we started with, how that was modified on the Thevenin's theorem to give us a simplified network. And that's what thevenin does. Okay. Now this is just a simple circuit. I have some which is more complex, but hopefully I will look at those at a different point in time. Now again, I hope you found this useful. I'm just going to cursor down again a little quickly. Okay. But please remember you can pause the videos yourselves, okay, as well. And I'll just bring it down to the end so that you can see everything in place. And that I have not missed or taken anything off screen. Okay, I believe that's it. Have a good day. Thank you. Bye for now. Bye-bye.